Our concepts for today are work, power, efficiency, and energy. We start by defining work. Work is the product of a force and a displacement. So a force acts on an object and moves it over a certain distance or displacement. And that is the product, rather, is the work done. And when work is done, there's a change in energy. And the work is equivalent to the energy change. Now, when we say a change in energy, we're talking about an energy transformation. And for each force, we can talk about what is the nature of that energy change or energy transformation. So for instance, if it's an applied force, if it's a person pushing on an object and doing work, then of course they are using the chemical energy stored in their muscles. So that's stored food energy, if you like. And they are making something move by pushing on it, using their muscles, and motion energy is kinetic energy. Another force of interest is the friction force, and friction force, when it acts on an object over a distance, changes motion energy into heat energy. So that is the energy transformation associated with friction. A gravitational force changes motion energy into height energy, which is potential energy, and also the reverse. That transformation can go either way. So you can throw an object up, and then you get kinetic potential. As it reaches the high point and begins falling again, though, that potential energy gets transformed back into kinetic. So work is the product of force and displacement, and work is associated with the energy change. Power is defined as the rate of doing work, and its units are joules per second or watts. Now, if we write power as work over time and then substitute that work is the product of force and displacement and then group that slightly differently, we recognize that distance over time is actually average velocity. So we can write the power in a slightly different way. We can say it's the product of force and the average velocity. Our final foundational concept is the concept of efficiency. Efficiency, we use a Greek letter eta for that. It's kind of like an N with a long tail. And it is basically a ratio of useful output to an input. Now, we have to compare apples and oranges, so it can be the amount of energy that you get out or the amount of power that you get out. The input can also be an energy or a power. So joules over joules, watts over watts. Those are all efficiencies. Let's try an example. So we're lifting a mass up at a constant speed over a certain distance. So first of all, we visualize. Here's the mass. So this may be, what would be lifting it? Perhaps a crane. It's 250 kilograms, so it's fairly significant mass, and so the forces acting on it will be the gravitational force straight down, and then whatever applied force is lifting it up. Now, 250 times 9.8 gives us a weight of 2450 newtons, and if we are lifting this at constant speed, then, thinking in Newtonian terms, constant speed means no acceleration. No acceleration means balanced forces. That means the applied force is just equal to the weight. So we can just type that out. So we can say constant speed means acceleration 0 means balanced forces. F equals the weight mg. There we go. So now we know how much force is being exerted on the mass, and now we can proceed with the task at hand, which was to find the work done. Work is the product of force and displacement. By the reasoning that we just went through, we know the applied force must be 2450 newtons, and we are lifting this mass a distance of 12.5 meters, and so we get 30,625 joules of work done. The required power. Well, powers work over time. We have the work, we don't have the time. Oh, but look, we have the speed. So it's going to be easier for us to find the power by multiplying the applied force times the average velocity. 2450 newtons was our force, 2 meters per second is our velocity, and that works out to 4,900. Now, a newton times a meter per second is indeed a watt, a joule per second. Finally, this 4,900 watts is the useful output of this project. That's the power of this mass being lifted up at 2 meters per second. The input to this process is given as a certain amount of electrical energy. So this electrical energy is, I suppose, powering a motor. So efficiency is the output power over the input power. So we have 4,900 watts of mechanical power, but we're using 10 kilowatts or 10,000 watts of electrical power. So we get an efficiency of 49, we'll just express this as a percentage, 0.49 of 49%. So there's a quick example of those foundational basic concepts. So work, power, and efficiency. Now, just a word about direction and polarity. You see, work can be positive or negative. It's not a vector quantity. It does not have direction, but it can be positive or negative. So what does that mean? Well, work, remember, is an energy change. So a force that's, say, in the direction that you're moving tends to make you go faster, tends to increase the energy, and therefore does positive work. So this force, notice here, F1 is in the direction of motion, so it will do positive work. There'll be an increase in the energy of the system. A force opposite to motion, say like friction, that is going to do negative work. That's going to reduce the mechanical energy of the system and slow you down. Now, in our relationship, where we have work as force times distance, F times d, there is no positive or negative polarity. We're going to have to remember to put that in ourselves. Let's look at another example. So we're pulling a 10 kilogram mass across a rough floor. So to pull it, there must be an applied force. This is a mu equals 0.1 rough floor, so there will be a force of friction opposing the sliding. And then, of course, we have weight and normal force. Round out the force diagram. This is a 10 kilogram object, so we have 98 newtons of weight, m times g. Forces will be balanced in the y direction, so the normal force will be equal to that. Why do we need that? Because we know friction is mu times the normal force. 0.1 times 98, there will be 9.8 newtons of friction. Now, if we assume that we are, we are not at constant speed, because in fact this force is 50 newtons. So we have an unbalanced force here, and this mass will be accelerating. So, part A of the problem asks us to find the work done by the pulling force. Notice that there's a 3 meter displacement here. So we are exerting 50 newtons over a 3 meter distance. So that's going to be plus 150 joules of work. So that would be an increase in the mechanical energy of the system. Now friction, because it is causing us to lose mechanical energy and slow down, does negative work. You have to remember to put that negative in to reflect a loss of mechanical energy by the system. And so this is minus 29.4 joules. So the total work done then, well, 150 joules of chemical energy in our muscles was used to do work on this object. And if that was the only thing that happened, we'd end up with 150 joules of motion energy for this block. But of that chemical energy, 29.4 joules was converted to heat by friction. So the resulting mechanical energy associated with motion is only 120.6 joules. Now there's another way that we could go about figuring that out. To find the total work, we could simply take the net force and multiply by the displacement. The net force would be the 50 Newton applied force minus the 9.8 newtons of friction multiplied by the 3 meters of displacement. That would give you the same value for the total work. Now, what's the efficiency of this process? Well, efficiency is a ratio of useful output to the input. Now, in this case, the output is the mechanical work, and the input, well, that's the chemical energy that's used, the food energy. So we had 120.6 joules of useful work done. That's the net total work, I should say, the total work done. But of course, we burned 150 joules of food energy to accomplish that. So the efficiency of this process is 80.4%. Now, in this case, we had to sort of remember that friction work was negative as a force opposed to motion. Is there a better way that we can set ourselves up to, I suppose, to have a slightly better, more useful relationship that builds that in from the start? And there is indeed. And we'll consider now the transition to two-dimensional forces. And that will get us to where we need to be. So this is a lawnmower problem. We are pushing on the handle. There's a weight force on the lawnmower. The surface will push up with a normal force. We'll be tending to move to the right, so there'll be friction to the left. And then this applied force is partly down with a y component and partly to the right with an x component. Now, forces that are perpendicular to the direction of motion, say, for instance, the normal force, the y component of the handle force, and the weight, they do no work. Because if there's no y displacement, then a y force isn't really doing anything to the energy of the system. Forces in the direction of motion do positive work, like this x component here. A force opposite to motion, like friction, does negative work. So how could we kind of build all of this chart into a single relationship? Just let me clean up this set of slides a bit. There we go. Well, we could refer to the angle between the force and the displacement vector. And we could say that the work done, if we wrote it as F cos theta times d, then we would capture all the information in that chart above. Why is that? Well, let's consider that angle theta between the force vector and the displacement vector. Just let me again improve this slide. There we go. Let's make room for it. There it is. So this is just on the next page in your notes, but I'll just put it on the same slide. Here's sort of the diagram that I have. Now, if we had a force that was in the direction of motion, then obviously that is just 0 degrees between those two vectors. And if we were to say, use the relationship that we just wrote down, F cos theta times d, Well, the cos of 0 degrees is just 1. So as expected, we would get work is positive F times D. Let's look at, say, the case where the force is opposite to motion, like friction. Well, the angle between those two vectors is now 180 degrees. And the cosine of 180 degrees is negative. So we would naturally have a negative sign emerging in this calculation of work. Now, furthermore, here, with an angle of 90 degrees, a force perpendicular to motion, if we calculated using F cos theta times D, well, we'd have the cos of 90 degrees, which is 0. So what we see then is all the information that we need is sort of correctly captured by this relationship. So this is sort of an efficient way, an efficient shorthand. It's an accurate representation of the relationship between work, force, and displacement. So in this lawnmower problem where you have some angle theta, if you need to find the work, well, you have to find the component in the direction of motion, right? So that's going to be F cos theta times D. All right, so that is the basic theory of the relationship between work, force, and displacement. So we've arrived at sort of this slightly more formal, but all-encapsulating definition, F cos theta times D. Now, the next thing we want to consider is what happens if we have a force that's varying, that's not constant. And so a typical case of that would be an elastic force from a spring. So we know that as you stretch a spring by Hooke's law, the amount of force varies. So the Hooke's law expression, F equals kx, again, sorry, slide tending here, would apply in this case. Now let's look at an example. Let's imagine that we have a spring with a spring constant, an elastic constant, K, of 1.5 newtons for every meter of extension. So that means as we start to pull on the spring, there would be 0 newtons of force in it. And for every 1 meter x of extension, your force would go up by 1.5 newtons. So for every 1 meter extra of extension, there's 1.5 newtons extra of force that's required. And so if we were to, say, plot that, as we often do in sort of Hooke's law experiments, for every 1 meter of extension, so 1, 2, 3, 4, 5, yes, okay, so this is force in newtons. For every 1 meter of extension, there'd be 1.5 newtons of force. And we can see that we're going to get a nice straight line out of that. And the equation of this graph is really just Hooke's law. It's F equals kx. And the slope of that is 1.5 newtons per every meter. That is the elastic constant, the k value. That's what the slope of this graph gives you. But let's look at not only the slope of this graph, but also the area, and think about what that tells us. So if we look at, say, the area up to 3 meters here, and I'll just draw the shape right here, well, it's just a triangle. So we had 3 meters of extension, and from our chart, we know that there's 4.5 newtons of force there by the time we reach that 3 meters of extension. So because it's a triangle, it's just a half times the base times the height. And that works out to 6.75 newton meters, which of course, a newton meter is of course a joule. So this is joules. What is it telling us then? Well, it's telling us the work that was done in this case. So work equals force times displacement it wouldn't be well defined here because, of course, the force is changing. So which force would we use? So what we're really doing when we say find the area is we're finding the work, and it's really just a way of averaging the force over that distance, because the force starts at 0 and it ends up at 4.5. So on average, it's half of 4.5. So to summarize then, if we have a force that's varying, the way that we can find the work is by finding the area under the graph. Let's consider a few simple examples here. So if it's a constant force, well, then the area is just the area of a rectangle. It's just 3 newtons times 5 meters. It's just 15 joules. If we have a spring force given by Hooke's law, then we have to do a half times the base times the height. Notice that this k constant, or rather this graph, goes up to 10 newtons over 2 meters of displacement. And those are, by far the two most common examples. Here's another one where we have a linearly increasing force, say like a spring, and then something happens to the spring and the force no longer increases. We've reached a plasticity point. Now in this case, to find the work done, you would consider, first of all, the triangle, and then secondly, the rectangle. So this would be a half. 4 newtons is this height, and then there's 2 meter base. Here it's 4 newtons of height, and the base goes from 4 to 2, which is again just 2 meters, right? This is just 2 meters. And so we add those up. This is 4 newton meters or 4 joules, and this would be 8 joules. So there'd be a total of 12 joules of work. So when we have a force that's varying, we can find the amount of work done using the force distance graph and finding the area underneath the graph. This is another way for us to find work, or rather another type of work problem. So to summarize what we've got so far, work is the product of force and distance, and when work is done, there's an energy change. To include all the possible orientations of forces, we should find the force component in the direction of motion, F cos theta times d, and this reflects the fact that sometimes work is 0 and sometimes it's negative. And finally, if you have a varying force, the work is the area under a force distance graph. Now the final thing we'd like to do is explore in a little bit more detail this relationship between work and energy. So we're going to start with a little derivation. So we did say that work was an energy change. We want to elaborate on that a little bit. So let's consider, as first case, just throwing an object. So in this case, our chemical energy is being converted into motion energy. So we know that the work that we did would be the product of force and distance. But if that force is the net force, then the force must be equivalent, F must be equivalent to ma. I'm just going to rearrange that a little bit. I'm going to write 1/2 ma. I'll put the a over here. And then times 2 ad. Now those two lines are mathematically equivalent to each other because the half and the 2 would just cancel. Why would you bother doing that? Simply because twice AD is VF squared minus VI squared. And so if we expanded that bracket, we would see that work is the change in this quantity 1/2 mv squared. So what this is really telling us, or what it's really giving us, is a way of calculating the motion energy or kinetic energy of an object. It's 1/2 mv squared, where m is the mass and v is the speed of the object. So sometimes when you do work on an object, you give it motion energy, kinetic energy, and that we calculate using 1/2 mv squared. Now, sometimes when you do work on an object, you can lift it up and give it height energy. So let us find an expression for the amount of work done here. Work is force times distance. Now, if we lift it at constant speed, then we know our applied force is the same as the weight. And if, as in the diagram, we look at the distance and see, okay, that's h, we get an expression then for the height energy. The height energy is energy h. Now, in the more general case, you can do work and you can give an object both height energy and motion energy. Like if you throw a baseball and look at it sometime later, it could have both height energy and kinetic energy. And in the even more general case, before you did work on it, it might not be at rest and it might not be at ground level. It could have some initial kinetic and potential energy. And we could say the kinetic and potential energy at the beginning plus the amount of work done will equal the kinetic and potential energy at the end. Now, the sum of kinetic and potential energy is the mechanical energy. That's the definition of mechanical energy. So perhaps a nicer, more user-friendly way to write this relationship is initial mechanical energy plus work done is final mechanical energy. Now, energy equations that follow from this result are just as important, just as useful as force equations, although we're perhaps not quite as familiar with them. So we're just going to take some time here now and actually write out some work energy equations. We'll do just using word equations, just using things like W and KE, so just symbols, not formulas or equations. But of course, eventually we'll want to solve problems, and there we will need to use our equations. But one step at a time. First, let's start by writing word equations. So here's our first example. And so in each case, we just want to write a work energy equation. So a person, in this first example, does work throwing a ball. So we look at the diagram. We say, okay, at the beginning it's at rest, so there's no speed here. And then it ends up moving. So our relationship is initial mechanical energy plus work done equals final mechanical energy. Now, there is definitely work being done by the throw, right? There's some chemical energy in the person's muscles that's being converted into kinetic motion energy. Now, what can we say about the mechanical energy at the beginning and the end? Well, clearly there was no motion at the beginning. There is kinetic at the end. But what about height energy? Well, we can, because it didn't change, we can just say this entire problem is just taking place at zero height, so there's no height energy to consider. So at the beginning, there's no mechanical energy. And then the chemical energy, that is simply being changed to the kinetic energy of the ball. Next example. So we have brakes doing work slowing down a car. So initial mechanical energy, well, it's moving. There's kinetic energy at the beginning. There's some work being done by the brakes. That's going to be negative, and that's associated with the heat energy. So it is negative, and it is associated with the heat energy. I should have mentioned this will be positive work. And the final kinetic energy that we get, you can see it's going to be slower, and so the final kinetic energy will be smaller. All right, so here's a slightly more interesting example. So we've got a cyclist pushing on the pedals, doing work, and moving up the hill. So at the beginning, there's no kinetic energy, there's no potential energy. So there's no mechanical energy at the beginning. So we say mechanical energy at the beginning plus work equals mechanical energy at the end. There's none at the beginning, zero. Now there's certainly some work being done by the person, and that's just a transformation of chemical energy in their muscles to something useful. At the end, the person is moving, so they have kinetic energy, and they've gained elevation. So there's also potential energy. Now, that was just, in that case, the bicycle was moving at the top. If you begin and end at rest, say like if you're in an elevator, then once again, you are starting at rest with no height energy. Some work is being done, say, by the motor, and there's some electrical energy input into that motor. And what we end up with, well, there's no motion at the end, so there's no kinetic energy, but there is height energy. So let's consider one final sort of word equation type problem, conceptual type problem. Here we've got a skydiver, and they're moving, and they open up their parachute, and the parachute slows them down. So this is the beginning, and then this is the end. So it makes sense to make this, even though they're not at the ground, you take the lowest point as the reference elevation. And so we'd say, okay, at the end, they've got motion energy. At the beginning, they had motion energy, and they had some height. And then what's doing work? It's the friction force, it's the drag force, it's the force of air resistance. And that's associated with heat energy, and it will also be a negative value. All right, let us next do a numerical problem, simple numerical problem. So here we're going to start with a cannonball at rest, and then the cannon is going to fire, and then a little later our cannonball is flying through the air 8 meters off the ground and moving at 10 meters per second. So our work energy theorem says the mechanical energy that we had in the beginning plus the work done will equal the mechanical energy at the end. Now, at the beginning, there's no height and there's no motion, so there's no kinetic energy, there's no potential energy. The mechanical energy of the ball is 0 at the beginning. At the end, it's 8 meters off the ground, and it's moving at 10 meters per second. There was work done in the explosion, and that represents the chemical energy in the explosive power that, when burned, was transformed into, we're assuming, completely into kinetic and potential energy. In reality, there'd probably be quite a bit of heat energy that's created as well. So we're just asked to find the work done in this process. So now we actually need to use the formulas. So we know potential energy is calculated using mgh, and the kinetic energy is calculated using 1/2 mv squared. So this is a 5 kilogram cannonball. The Earth's gravity field is 9.8 newtons for every kilogram. And we know that the cannon reached 8 meters of height. So that's 40 times 9.8. That's 392 joules of potential energy. For the kinetic energy, we've got 10 squared is 100, 5, that's 250 joules of kinetic energy for a total mechanical energy of 642 joules. And then that is the amount of work that was done on the cannonball in this launch. Now, if we think back to the beginning of this video, we said a work was a force times a displacement. Now we're saying, okay, it's an energy change. Well, really, at the beginning, we said both, right? We said that work was a force times a displacement. It's also an energy change. Well, why in the previous question of the cannonball, why did we not say force times displacement? Well, you see, that's still true, but we didn't know the displacement, really that's the length of the cannon, and we didn't know the amount of force that was being exerted on the cannonball. So we really didn't have a choice. We weren't able to calculate the work using force times displacement. We had to use the energy change. Well, in a final example, we'll show that if you do have the ability to do both of these approaches, they will give you the same answer. The problem that we'll consider is simply pulling an object up a ramp. So we are pulling it at a constant speed, and we're just going to find the work done. First of all, using the product of force and displacement. So, well, we know something about forces on ramps. We know that if we're pulling it up, and this is a frictionless ramp, so there's some tension force. The Earth pulls straight down. There'll be a normal force perpendicular to the ramp. And we have to resolve gravity into its components, the mg cosine theta component and the mg sine theta component. Now, since we have constant speed, we will have balanced forces along the ramp. And that means the tension force will equal the slide component of gravity, which is mg. In this case, it's an 8-degree ramp, the mg sine theta component. This component down here. So since we know the force, and hey, it's a 20-meter long ramp, right? There's the displacement right there. We can get an expression for the work done. It's mg, and I'll put in the fact that the mass is 250 kilograms. Mg sine of 8 degrees times 20. I'm not going to work out that number, since I simply want to do a comparison. I suppose if you really want to know the number, it's like 6820 joules. I have it here. Okay, so great. We were able to find the work done using the product of force and displacement. Well, what if we considered next change in energy? Let's find the work done using that approach. So we visualize, right? We're pulling it up at constant speed. So it's starting off at the bottom, moving at that speed. It's ending up at the top, moving at exactly the same speed. Let's write a work energy equation. Mechanical energy at the beginning plus work equals mechanical energy at the end. Now it's clearly moving at the bottom. There's no potential energy. We're doing some work, something's pulling it, I guess the motor, some sort, or a person. Up at the top, it's moving, so it's got kinetic energy, but it's also got some height. Now, the thing is, because the speed's constant, that kinetic energy is exactly the same as it was at the beginning of the problem. So although there's kinetic energy at the beginning and the end, it's not changing. So the work done, which is associated with the change in energy, is just due to the gained potential energy. And we know that potential energy is mgh. And so what we really need to know is how much height do we have here? Well, this is just a triangle problem because we know it's a 20-meter displacement. And this height h is the opposite side. So it's 20 meters sine of 8 degrees. So let's put that in then to our expression for the work done. The mass is 250. We'll leave g as it is. The height is 20 sine of 8 degrees. And now let's take that expression and compare with what we had above. You see it's identical. That was 250 g sine 8, the force, times the 20-meter distance, so 250 g sine 8 times 20. This is 250 g times 20 sine 8, which is the same. So the point I'm making is that you can calculate work done using the product of force and displacement or using the mechanical energy change. In some cases, you have to pick one or the other, but in this case, where we were able to do it both ways, we got exactly the same answer, as indeed we have to, because of course physics is self-consistent. So this concludes our introduction to work, power, energy and the relationship between them.